Greetings, everyone. Welcome to the third conference on Applied Geodesic Engineering hosted by the Society of Geodetic Engineers, Geomatics, and Surveyors of Venezuela, SIGGMA. I'm Dario Gonzalez, and it is my pleasure to facilitate today's section. As a member of our organizing committee, I would like to sincerely thank all of you for joining us this webinar presented by Mr. Nils Lundström, titled Managing Geospatial Integrity in the Ever-Changing Application Landscape. Nils is a graduate at both undergraduate, graduate, and postgraduate levels in computer science and engineering, and has worked with geospatial data in the aviation and hydrocarbon exploration industry. Nils is working closely with client in solving many data problems associated with all geospatial aspects of coordinate reference system integrity, particularly within software application. He's passionate about the data integration as well as forensically examining vintage data to explain causes and results. Nils is currently involved with numerous A&P companies to realize all aspects of geodetic frameworks alongside implementing tools to enable increased automation and control within workflow requiring geospatial integrity. Nils is also the product owner of a GeoRepository, a cloud-based solution for managing all the geodetic parameters required to fully maintain and control complete catalog of coordinates reference systems and coordinates operation. We will address any comments or questions related to today's presentation at the end of the session. Please submit them in the question section. Thanks, Nils, for joining us of the third conference on Applied Geodesic Engineering. Welcome, Nils.
Thank you very much. Can you hear me now? So we are sure.
Yes, we can hear you.
Okay, perfect. And everyone can see my presentation that's up and running.
Yes.
Okay, fantastic. Let's get going then. Let me just press the right button. Right. So here are the contents of what I intend to actually talk about today. So I'll start with the introduction and the definition of geospatial integrity. Then I am going to touch on the history of geospatial integrity and the reasons why we need to look into this more specific. I'm also going to talk about a number of solutions of how we can then manage this geospatial integrity, mostly among all the applications that we use today. And as you heard in the introduction, I work mostly in the oil and gas industry. So all of the applications that I am going to talk about generally are used in oil and gas industry. A few of them you might use elsewhere, such as Blue Marble or the S3 ArcGIS tools. Let me go on. My mouse isn't responding as well as I would like, but there we go. Right, so just to begin with, definitions. Geospatial. We define that as something that relates to the Earth or the Earth's surface, or in our capability of oil and gas, close to the Earth's surface. And when we talk about integrity, we also can mean that in a number of different ways. But if you see the screen here, we are going to use the second definition of this, the state of being whole and undivided, which means that geospatial integrity really is about something that relates to the Earth's surface and that doesn't change. So it's rather immutable.
Nils, sorry, yes. Nils, we cannot see your presentation.
You cannot see my presentation now?
No.
Okay. I wonder what happened.
Yeah.
Can you see it now? I reshared it from the application.
Yes.
Right. Fantastic. Great that you interrupted me. Otherwise, I would have gone on. It's funny when you don't have a feedback. Right.
Yeah, right.
What we're going to talk about now is geospatial integrity in 7 steps. So let me just go and change the screen again. So yeah, just interrupt me if something goes wrong. I see on the webinar that sometimes there's a red, there's some kind of red thing flashing up. Maybe that's saying you can't see it. Let me keep an eye on that, see if it comes up. Anyway,
Okay.
geospatial integrity in 7 steps. So geospatial integrity is a concept of consistency in, first and foremost, our values. And our values is really what is important to us at the moment. When we look at geospatial integrity, mostly that's coordinates or data that is georeferenced in some way. But with those values, we need something that we actually call principles. And the principles are fundamental truths. So we are going to talk about these individually going forward, but this is the undivided thing that we have, which is always true and that cannot be changed. Now, our principles will also lead to something we call measures. And the measures are basically plans of actions or things we can, how can I phrase this? Things that we can measure, basically. How do we, oh, let's just go on and see that in the next few slides, what I actually mean. Now, on the measures, when we have those in place, we can use a number of specific methods to handle our data. And the methods are single procedures. They all make up actions. And actions are chains of the particular methods that we use to modify our geospatial data. Now, when we have these actions, we can then start defining what our expectations are. And our expectations are what we want to see in our different applications. So if we have data in one application and we apply our actions to get the data into another application, we can then define what the expectations should be on that application. So basically what we want as a result. And the end step of all of this is called the outcome. And the outcome is defined by what we actually get when we do this. So we have to go through all these 7 steps in order to make sure that we are good in doing what we do, and all the things that we apply to our coordinates or the data that is geospatially positioned. So how do we do this? Well, if we look at the actual data that we have to put in place what we call here some human constructs of accountability. We have to believe that people do the right thing to the data, that they apply the right applications, and that they follow the internal workflows that a company have set up. And they need to do that consistently every time. And if they don't do that, then the chain breaks down and we will end up with results that are vastly different from our expectations. But if we just look at the applications, and we can look at that objectively and using scientific methods, because the applications internally will have algorithms put in place. They will handle different types of values. They will be floating point values, or they will be integers, etc. All of that we can judge using scientific methods, and the user cannot really do anything about that. So if we can combine all of this, we can make sure that we maintain our geospatial integrity as the data flows through a plethora of applications that we use. So if we now come back to what we called our principles, or our fundamental truths, what we have in the geospatial domain is a piece of data which is generally a coordinate. Here I'm putting up the X's and Y's and the eastings and northings, or the latitudes and longitudes, as a two-tuple, or we call it a tuple. These can obviously be one tuples and three tuples as well, because sometimes we have a vertical coordinate reference system applied as well, and sometimes we have a 3D coordinate that we need to deal with. But generally, we are talking about two tuples, or X and Y's, or eastings and northings, when it concerns the applications we use in oil and gas today. And then we go to a single vertical CRS when it comes to wells. What we all know is that a coordinate such as this is worthless without a coordinate reference system. If you don't tell us what coordinate reference system this X and Y is, then there is no way we can say where this is on the globe. Therefore, we have no spatial integrity, so we need a coordinate reference system with this. And that introduces a little bit of a problem to us. And that is then the consistency of our principle. Because if we say that it's a coordinate reference system, that coordinate reference system, it represents a number of parameters. I'm not sure how much you know about how a coordinate reference system is made up, but it contains ellipsoid definitions, prime meridians, datums, coordinate systems, and a lot of parameters on conversions, if it's a projective coordinate system. All of that, it just sits behind the name when we deliver a coordinate. So if we have an X and Y, or an easting and northing, and we say this is WGS84 UTM 15, then we haven't actually been communicating what the parameters behind that CRS is. So we need to solve that in some way. And what applications do is that they use coordinate reference system catalogs. And these coordinate reference system catalogs are basically created in different ways. And sometimes we have programmers who are not GIS engineers in any way, shape, or form, and they don't understand what the values that they stuff into the database actually are, or what they represent. Which means that we have a lot of different applications currently that have different implementations of the CRS catalogs that contain different types of data, which we are going to see going forward. Now that we've defined this, let's go back to what I called the measures before and formulate that. So the measure that we are going to look at here is what it says basically: whenever we look at positional information, the same named point shall always be geospatially at the same location. In essence, what it means is that if we go out and we survey a point, and that point then travels through a number of applications, and it goes through a number of different conversions and transformations, and even get expressed in a different coordinate reference system, that shall always still point to the same point on the Earth. Now, that positional information is then represented by the ordered set, and the ordered set is the coordinate tuple, and the metadata that we send with it, the metadata being the coordinate reference system definition. In most cases, that's just a name, as most people actually know. So going forward, let's just talk about this and say that when we say a coordinate, we mean that it has a CRS with it. So when I say a coordinate in the future of this presentation, I mean a tuple together with a CRS. All right. Now, being able to do things with this produces another problem, and I call that hello equivalence. Because if we have coordinates that are the same, they represent the same point on the Earth. How are we going to compare these? What do we do? And the way most of the applications deal with this is to implement something called a bound CRS, sometimes referred to as an early bound CRS, what it means is that we tie a coordinate reference system such as NAD27 together with a transformation. And the transformation destination is another system called WGS84, which is a global system. And we then say that all these applications, they deal with equivalence on WGS84, meaning that if you have a point on North Sahara 57 or SAD 69 or as we see here Beijing 54 with a kind of projection, and you believe it's exactly the same point as another point in ED50, for instance, you transform both of these to WGS84 and then compare them on WGS84. And that's when we say we have equivalence on the WGS84, ellipsoid or CRS. The operation is called, or the applications that do apply this, they're called hub-based applications. And I would say that every CRS or every application I've seen so far during my work has been having WGS84 as the hub CRS. So if you look into coordinate reference system catalogs, you will see that most of the catalogs have everything defined with a transformation to WGS84. I've got some examples down there which are from the oil and gas, Petrel, OpenWorks, and Compass. For those of you who work in oil and gas or with that, you'll know what it is. They all have CRS catalogs or coordinate reference system catalogs with transformations to WGS84, and they have locally used the bound CRS as a CRS, really. So not only having a CRS definition and the tuple, but also having a transformation tied to it. All right, once we have this way so that we can actually compare coordinates, we can then define the operations or the methods that we can apply to these coordinates or to the geospatially referenced data. And we call that the methods. These are generally coordinate operations. So we operate on the coordinates, and we have two types, a conversion and a transformation. A conversion is generally applied when we have no change of datum, or we could be bold and say no change of the base CRS or something. So if you look at a WGS84 UTM 52, we can go from UTM 52 to 53 by a conversion, but they're still sharing WGS84 at the bottom. When it comes to a transformation, we have a change of datum. So we can transform coordinates from SAD 69 to PSAD 56 or things like that. So basically when we have a change of datum. Once we are capable of creating or doing these processes, we can then put them together in chains, and those chains will then become our actions. So our actions will allow us then to compare the coordinates, for instance. And if you remember what I said, we have coordinates in local coordinate reference systems. We then apply a number of methods to get them into WGS84, and on WGS84 we can then compare these coordinates. In the same way, these actions are really what's going to happen in the applications when we go from ArcGIS into Petrel, or from Petrel to a database, or between other different applications. It could even be between scripts of programming languages, etc. Then they apply these actions. If we have defined everything well and we know what the workflows are in the company, then all of these should be done in the same way and consistently in order to maintain our geospatial integrity. So that was a little bit of an introduction to this. What I'm going to talk about next is really a little bit of the history. And as some of you will know this, I'm sure, others will probably not. But historically, we had computers. Well, historically, we even had just paper and no computers. But let's talk about the computer era, really. Computers were on desks, they were not connected, we were pre-internet. We also had problems with defining the coordinate reference systems correctly. We were just looking at text-based systems, etc. And most of the machines were simply a copy of a piece of paper which represents a coordinate system rather than a coordinate reference system. And we call that to be geospatially unaware. And ArcGIS, for instance, was geospatially unaware when it came out to begin with. AutoCAD is another one that were geospatially unaware that has changed over time. Now, today's applications are geospatially aware, however. They follow these principles that we've gone through. We can share the data, we know where the data is, we can plot it on a piece of map, we can go to Google Maps and put in our KML files that we can get out of our applications, etc. But basically, anytime you enter some kind of data into a geospatially aware application, it is going to ask you what is the coordinate reference system for this data that you want to put in. And if it is displaying data, it is most probably also going to ask you to give it a transformation to the common CRS that it displays data on, unless it's using bound CRSs where you have well-defined transformations to WDS84. Now, when we go further, we don't just want to have our data sitting on our desks, but we now employ databases. So we have geospatial databases that serves hundreds of users, and they are viewing the same data. They are viewing this data in different applications. Remember, these different applications have different coordinate reference system catalogs. They have different sets of parameters representing the CRSs. How do we make sure that these applications actually show the position of our data in the same way and at the same point? We also have single applications that superimpose data from multiple sources. So we have these layered applications. You probably use that very often by importing maps. You have Google Maps in the background of your project that you work with. You may have LiDAR data coming in. You might even add 3D data, etc. All of that data needs to be visualized in some way, and it needs to be visualized in a common CRS in some way. And again, our 7 principles that we discussed earlier will come into this and make sure that data is displayed in the right position. The last point here is that once you start setting up your project, you start working with your data, you actually want to share this with other users. Other users may be using different viewers, so you are now transferring data not only from a database, but directly between applications as well. And at that point, we need to make sure that those applications actually understand the parameters that are behind the coordinate reference systems that are used in the different applications. So it's being more and more complicated, this, and it requires a huge amount of consistency and sometimes also a bit of automation to be working very well today. We also then share data externally, specifically in the oil and gas business. Our data is very valuable, and we tend to sell this data. We divest or we buy data from others. Therefore, we will end up having data that are referenced to other companies' coordinate reference systems. Sometimes they are even local coordinate reference systems to the company only, and at that point, it becomes important to understand what the parameters are with that CRS. Otherwise, we will not be able to correctly position that data. And one should remember that when we're talking about oil and gas companies, the reserves of oil is basically what makes up the price of the shares, and reserves of oils are calculated based on positions. So if you have an oil field that is 25 kilometers long, for instance, and 300 meters deep, and you have positions that are 20 meters wrong, then there's a whole lot of oil that you are losing to your competitors that are causing devaluation of your company. So having the data geospatially correct is of utmost importance to the valuation of the companies. Data can also be remodeled in some way. We are talking about pictures, images. They are transformed in some way. How we transform them and correct them is also dependent on the parameters that sit behind all the CRS definitions. So the problem that we have in the oil and gas business, and possibly in other companies as well, is that we have many CRS catalogs. As I mentioned before, we may have a CRS catalog per application that we use. Because we transfer data between these applications, CRS information is being copied between the different CRS catalogs that sit behind the different applications. These catalogs will use different units, as I've got some examples here. They will, some of them will use radians, some will use US survey feet, others will use degrees or seconds of degrees. So we need to be able to do that very well. And again, we're looking at the methods and how can we make sure that our applications actually do the right thing. We also have the actual values in our pair, and if you remember, I mentioned that these are ordered pairs. The coordinate reference system, or the coordinate system, actually defines in which order these coordinates should come in the tuple. So if you have an easting and a northing, that should be east and north. But other applications use north and east, and we need to make sure that they handle that in the correct way. Otherwise, we might throw around the positions and we will lose our geospatial integrity. We also have what's called bespoke CRSs, or user-defined CRSs, generally in the US. These are CRSs that are created by the oil and gas companies when they go into a new area, and they usually don't share these with other companies because they don't want to tell other companies where they are going and looking for oil and where they're doing exploration. At some stage it will become obvious, but initially they are kept very close at the chest. Also, when you then send this data from one application to another, it's imperative that the new application understands the parameters that come with that CRS definition. And sometimes they simply don't, or they assume that you are talking US survey feet, or you're talking ppms for your scales, or things like that. So you end up with a plethora of user-defined CRSs in your different application catalogs. That may or may not actually have the same parameters and may or may not convert the coordinates or transform the coordinates correctly. The effect of all of this is uncertainty. So you are going to get uncertainty in selection of a coordinate reference system because most of these applications only show the name. And if the names are not being correctly transferred across, or if people are going to name their CRSs oddly, then you don't actually know what's behind the CRS, and you can't actually make an informed decision as to what CRS you should select. And it leads to people generally selecting the first CRS in the list, causing lots of problems. The other thing here is going to be the uncertainty in the positions, because you are going to have a loss of geospatial integrity. And the last one is an increased CRS catalog chaos. Because CRS or applications can't actually identify the different CRSs correctly and say, I have this CRS in my catalog already, you are going to see duplications of CRSs in your catalogs. And basically, whenever people are going to select things, it's going to be just a nightmare to select the right thing. So I think the last slide for this part here is going to go on what factors actually implement or affect the geospatial integrity. And the definition of units is one that is of utmost importance, really, because everyone likes to use SI units, but SI units may or may not be the answer to everything. If we look at radians, for instance, we always need to use the value pi when we convert from radians to degrees. We are talking about axes that go out from the center of the Earth to the crust, which are, sometimes in the region of 6,000 to 8,000 kilometers long, having small values, trigonometry, and values like pi will cause issues in your applications because they are built with programming languages, and programming languages deal with floating point arithmetics differently. They have different number of decimals, they have different number of bits, and you simply get smaller differences when you do these transformations or conversions. You're also going to see the application data structures coming into this. How am I storing my CRS definitions in my application? Am I storing everything that I need? Am I storing this as well-known text, for instance? By some, it could seem like a very good idea to do that, but eventually you'll find that you are lacking smaller pieces that you actually need. The next one is the implemented algorithms. So how does your application actually do the calculations? That's very important to look at. Do they follow the mathematical algorithm that was described by what document, for instance? We're also going to see what's called areas of use, because our transformations generally are from the local CRS to the global CRS, and they are generally defined over smaller areas. So they are approximations. Are we using them in the right area, for instance? Are we staying within our area? What is the stability of the algorithm when we are inside and outside the area? You can just look at NAD27 conversions using NADCON, for instance. It's a very well-defined area. If you go outside, the algorithm doesn't work because you don't have any data. But if you have a 3-parameter geocentral or geocentric shift, you can use it across the world, but it will not make sense if it's outside the area. You also need the correct CRS identification. So when you load data into your application, if you select wrong CRS, then your data goes off by a little or a lot, depending on how wrong you select the CRS. And you pray that your CRS catalog, once you've selected that CRS, does actually have the correct parameters. If it doesn't, then it will affect your geospatial integrity very much negatively. So that gets us into solutions. And the first thing that we generally look at is geodetic entities names. You remember I said that people tend to name the coordinate reference systems funny or doing their own thing. I've seen Pete's US CRS, for instance, got some examples here. North Africa 1, Algeria UTM 32. We can guess that it's a real UTM conversion behind this, but we don't really know what the base CRS is, if it's North Sahara or if it's Voirol or something. So it's very important. Behind these names, we also have all these parameters, and we get into all sorts of problems when we don't have control over this. So the first thing that we do is actually change the naming and make sure that people follow some guidance on the names. And there is an organization called the IOGP, which actually provides documentation or guidance documentation. In this case, we are talking about a document called 37307-6, Policies and Procedures, Data Naming Conventions. This is a good document that, in essence, gives you all the guidance you need in order to name a CRS that you create. And when you name the CRS in the way that the document describes, then you can also identify the CRS later as to what it actually is and what should be behind the parameters. The examples here being PSAD 56/TM56 Southwest. This is a projected CRS that's indicated by the slash. That has PSAD 56 as the base, geodetic or geographic 2D CRS, and then it's got a conversion based on transverse Mercator with a central meridian of 56 degrees west, and it's a south zone, so it's actually valid for the south hemisphere. So from this, if we follow some other guidance from this, we can actually judge, or we know basically what the parameters behind this conversion will be. The last example we have down there, where it says ED50 star EPSG NOR N62 2001 with a bracket and some numbers, is what's called a bound CRS. And this is a bound CRS of geographic ED50 2D together with a transformation. And this transformation is given by a description string. So it's created by EPSG. It's valid in Norway, north of 62 degrees, and it was created in 2001. And then the numbers behind there are actually numbers into something called the EPSG registry, which we will touch upon shortly. So once you put in some guidance of the naming, you know how people in your company are going to name things, then those names mean the same to everyone, and all the applications should expose the same names in the CRS catalog, and they should be then indicating that the parameters are correctly behind that, which makes it easy for a user to select the right CRS. Now, names are generally difficult when it comes to databases, so we use something called codes. We always associate a code, a numeric code, with an entity, and they are very often used as the key to the data in the database. And remembering the previous slide where we saw the bound CRS, those two codes in the brackets actually identify the CRS. So they are implicit in defining the data. Applications know this, so applications such as ArcGIS use codes for all their CRSs, and they allow users to add their own CRSs as long as they use 200,000 and above. All our other applications such as Petrel 700,000 plus, EPSG CRSs need to be above 32767 if they are user defined, because everything below the EPSG registry reserves for themselves. There is guidance on this as well in the same document, and it comes up as policy for entity codes. And you see that I've marked that 4230 and 1612. We can see that in the registry later. The little table I have there indicate how this is handled in companies. So in essence, companies, when they create their own CRS catalogs, they need to create all these elements that are listed here: scopes, naming systems, ellipsoids, prime meridians, etc. All of that is included in creating a coordinate reference system, or specifically a bound coordinate reference system. So they define in a document the codes that they are going to use, And then sometimes they also define how these codes are recalculated for the different applications, which means that all the people in the company, when they see a code, they can immediately go to a central registry and put this code in and then get some information back and see what the CRS is that we use. And that gets us to basically the next step, which is called the EPSG registry. Some of you will have seen this registry, others will probably not know what it is, but the EPSG registry was created in 1985, and it's called the EPSG registry because it was a collection of companies in Europe that set this up. So EPSG is short for European Petroleum Surveyors Group, and it was they all came together and said we need to have a central registry so that when we share data with each other, we actually know what the CRS definitions are. And if you tell me that I'm using code 32635, I can go to this central registry and pull out all the data I need and then create that in my own CRS catalog or in my own applications. So this then became public in 1993, and shortly thereafter it was put on the internet, and then it became a de facto standard, really. So when we talk about EPSG codes today, almost everyone know what we mean. And if we work with companies such as OGC, for instance, OGC will refer to EPSG for codes of CRSs. So if you use ArcGIS, or if you use any other GIS application, it is a huge likelihood that it will, in the background, actually talk to OGC servers who will forward the question about parameters to the EPSG registry. The EPSG registry approach is also ISO based. So ISO, which is the International Standard Organization, has gone about and created a document called 19111, which is called referencing by coordinates. And this basically breaks down a coordinate reference system into all the smaller parts that we need to have in order to correctly define this CRS. And the picture I have at the bottom there is taken from the EPSG registry, and it basically shows all these tabs where you can see the individual parts. So the EPSG registry bases its data model on the ISO standard, and anytime we look into data, we can see that data. So I was thinking that I should just quickly jump over to that website and have a quick look. Oh, so it says SIGGMA. Okay, it's actually wrong. It should say epsg.org. So my fault. Right, let me go to epsg.org. This now shows, right? I'm going to assume that it does, right? So this is the EPSG registry. It's online. It's available to anyone. It's a public site where you can go and look at your CRS definitions. All the CRS definitions will be below 32767. That's a finite number of codes that they have that they can deal with. If we look at the text search, for instance, it will actually give us the entire data set first. You can see the tabs here. So this registry contains 7,033 coordinate reference system definitions. It contains 2,518 transformations. It contains point motion operations, concatenated operations, conversions, datums, and then you can press this little button saying more. Which allows you to then look at coordinate systems, ellipsoids, prime meridians, extents, units. It will also include the coordinate operations. So you see coordinate operation methods here. We can go in and we can have a look at transverse Mercator, for instance, and we can get to understand how that is actually done. Now, if we simply go and select the CRS here, let's just select this first one. It's actually going to come up like this, and we can now start drilling down into the coordinate definition. And we can, the first thing that we see is something called a usage, and that usage has got a little polygon with it where it will tell us. There should be a base map on the back of this, so I'm assuming that something is not going right at the moment, but let's just carry on and see what happens anyway. The coordinate system, oh, there you go, it's just a bit slow. The coordinate system that we have here is a Cartesian 2D CS. We have easting and northing, so we are very specific in the order of our coordinates. You remember the tuple we were talking about. The base CRS that we have here is Abidjan 1987. That is based on Abidjan 1987 datum. The Abidjan datum may have a different usage than the actual CRS. This is based on an ellipsoid. This ellipsoid is Clark 1880 RGS with the definition parameters here. We have the prime meridian Greenwich where we have the 0 degree partition, and if we close down that one, we can see that the conversion is UTM zone 30 north. UTM zone 30 north has a different usage. We should be able to get still no sound?
Yeah, I can hear you. It was frozen.
Hear me now? Yeah, it was frozen. I noticed that the network went down somewhere.
Okay, you can keep going.
Do you still see my screen?
Yes.
You still see my screen, right? Okay, so we have the usage here of the UTM conversion coming up. We got all the parameters that we need here. And we can then go and create a printout of this. If we want to have that data, we can look at the well-known text. If we were to create a CRS in an S3 application, for instance, we can get this well-known text, the GML, which is another way of defining CRSs. Now, not only that, we can search for data using map searches here as well. We can go in and select a point, and it will go and find all the usages that I showed that actually sits beneath that point, and then show me all those CRSs. We can go in and define a box or a polygon. We can certainly zoom in, and obviously something.
Sorry, Nils is frozen again.
Can you hear me now?
Yes.
Odd. I noticed that it was zooming out. All right, so you can go in and basically define a polygon such as that and go and search for that, and it will tell you everything that is. Now, I'm seeing that red bar flashing on my screen. Does that mean the page is frozen again?
No, we're hearing you, and we can see your screen. Nils, can you hear us? Yeah, we can hear you, and we can see your screen. Nils, sorry, your microphone is mute.
You hear me now?
Yes.
Okay. Sorry for these troubles. I don't know what's really going on. Right. So in essence, this application here, which is then a cloud application, allows you to maintain or verify coordinate reference system parameters very easily. And most of the oil and gas companies actually have their own version of this. So they don't generally use the PSG registry such as this public one here, but they have one themselves on their own servers where they have all their own bespoke or custom CRSs defined, which is just exposed to themselves. Now, this single catalog here, in essence, feeds all other applications then. Because they download. So this application allows you to download the data from here as either an Access database or a SQL Server scripts, but it also allows you to talk to the application in the background using API calls. So applications such as Blue Marble, for instance, they talk to the PSG registry and refreshes the parameters from there. Occasionally, or even when you as a user want to do this. So going back to the presentation, we will be here, there, right. So at this point then, we have a coordinate reference system catalog with a known structure, which is based on ISO recommendations. We have defined our naming structure so that our people in the company knows how to name their CRSs, they know how to select the CRSs, and then we have defined a numbering range so that we know where our bespoke CRSs or our custom-made CRSs are going to be inside or in this range. That allows us then to create and distribute what we call parameter sheets. So when you send data to someone else, you can go in If you'd hear me now again. Yep.
Yeah.
So you can go in and send that piece of paper together with the data to whoever receives your data, and they will be able to then put that into their own application. So you can also use this website then to guide and communicate with your users. You can send them links to the information that is immediately available at hand to them. The thing that we don't yet understand, however, is how applications deal with this. Do they understand this data now that we have it defined? Do they understand what the parameters are supposed to mean, and do they follow the right algorithms? And we do that. So I'm seeing that I'm taking far too much time.
Yes,
we do that. We have a bit time more. All right. So we do that with something called GIGS, which is called Geospatial Integrity of Geoscience Software. So I'll speed up a bit. This here is a way that we are guided in determining whether our applications do the right thing. We have a guideline on how to do some testing. We have detailed technical procedures of how to do these tests, and we have a test data set. And when we use this, we basically understand what functionality our application is capable of. Is it capable of doing conversions, transformations? Is it capable of having user-defined CRSs, for instance? And then does it do it in the right way? So the GIGS test data set includes a lot of positions and a lot of CRS definitions that you run through your applications. And they will then come back and say, hey, this application performs within 3 millimeters of the expected output, or this application doesn't actually do NADCON transformations, or this application doesn't allow you to do bespoke CRSs. So once you have that, you actually have control, in essence, over that. You can define your CRSs, you have your coordinate reference system catalog, and you know that your applications, whenever they are implied in doing any of the processes, the methods that we spoke about, and the chains of actions, they are going to do it in the same consistent manner every time you do it. So that works very well. I'm going to skip actually showing that. So the last thing that we need to talk about here then is the user. So the user needs to have, and let's do this little quickly, workflows. So whenever you put everything in place, you need to have acceptance from the user that, hey, we have this documentation, we have these catalogs that we are using, and we have these defined methods that we use to transfer our data. Now, in order to be consistent, you need to use these every time, and you need to follow this and do it the right way. Once the user does that, he then assumes the responsibility of doing this correctly, and that's when we achieve the geospatial integrity, basically. So at the moment, we have our geodetic parameter catalog, we have our uniform naming, we have the understanding of how applications perform these computations, we have the workflows, and in short, we then have geospatial integrity throughout all our applications. Now, going forward, we have the future, cloud-based applications, which some we have seen. We have RESTful or other stateless APIs that we can talk about, and we have a high degree of automation and potentially some verification against the truth at some stage, but we are not there yet. However, we are there already. We have cloud-based solutions. We saw the EPSG.org, for instance. We have cloud-based calculators. So this is an example of a calculator that selects data from the EPSG registry. So it basically takes all the parameters directly. We have seismic binning grids applications in oil and gas that talk directly to the EPSG registry or to the company's own registry. We have a well application in the same way that talks to the EPSG or the company's own registry, and we have ArcGIS Online, for instance. That is another cloud-based application for this. We also have RESTful or stateless APIs. I'm not sure how many of you use this, but the first one here is from OGC. This is a way of using HTTPS or HTTP to get a definition of a CRS. You can do that from within your own applications. We can use the Georepository API, which the EPSG has got on their web page, and it looks like this. So you can basically go in and start querying data without actually having to touch the user interface. We also have an API for the calculator, which allows you to do geodetic calculations immediately online without having a calculating engine in your own machine. So we have all these APIs, and all the different applications inside the different companies then can make use of these APIs, which then talks to a central database, which means that we have full consistency in the parameters and we have full consistency in the algorithms that you use. together with this, we put in a little bit of automation. And you can now start using your JavaScript in HTML pages, or you can use Python, for instance, to directly talk to these databases that we've set up. The last step that we go through is then the recap of all of this. So you have your business rules. We defined our principles, the absolute truth. We defined our methods that we had. We then went on to define our naming conventions, with ISO compliance. We put in a central geodetic registry, which contains all our parameters and all of that. And we have the GIGS testing to make sure that our applications actually do the right thing when we use them. And in the end, we have the automation and the actions that we defined as chains of methods that we use. That then make sure that we have geospatial integrity throughout the entire plethora of the applications that we use on a daily basis, at least in the oil and gas business. That gets me here. The questions.
All right. Thank you so much for your excellent presentation, Nils.
Thank you.
Yeah, so insightful presentation. Just a reminder for all our audience, you can submit your question or comments in the question section. So I already have a few questions. The first question is, what challenges arise in maintaining geospatial integrity as an application evolves?
One of the major challenges that we see is something called deprecation, because the data, the CRS catalogs evolve over time, and we sometimes have used CRSs that are incorrect. Once a CRS is incorrect, actually the definition of an incorrect CRS is something that causes an error of 3 millimeters or more, I think, in the UPFT dataset. Some of those CRSs are being corrected, and when they are corrected, they are being deprecated, i.e. they are not deleted, but they are removed as being invalid. Applications that we have today cannot cope with it. So we have a lot of CRS catalogs around in the companies in different applications that still maintain invalid CRSs. And that's a huge challenge for us to deal with that going forward, because there's going to be an increasing number of CRSs that undergo changes in their definitions, especially in the companies where they use bespoke or user-defined CRSs.
Yeah, correct. Interesting. So how can emerging technology impact or improve geospatial integrity management?
I think we're going to see a lot more automation going forward. We're going to see a lot more scripting. Like I said, JavaScript, Python. We're also going to see ChatGPT coming in, AI, being able to draw information or combine information from different databases. And that's going to be a huge challenge as well, because we need to make sure that all these processes are validated in some way, similar to the 7 steps that we spoke about earlier.
Yeah, correct. Yeah, the third question is, how can automation of real-time data updates helps in preserving geospatial consistency?
I'm not sure if it helps really. We have live data coming from drilling sometimes. We've got live streams. What we need to make sure with those live streams, again, is that they actually follow the consistency rules. And we've had a number of projects where we've implemented live streaming of data, where we found that the processors sitting between the applications weren't actually doing the right thing, and we were simply saying that we need to have static CRSs, or we can't actually change CRS between the applications. So if we're using SAD69 UTM something in one application, that's the same CRS we have to use in all applications downstream from that one. So I'm not sure live data can actually affect the geospatial integrity, but it can ruin it.
Yeah, yeah. So the next question is, what is the risk of not maintaining geospatial data integrity in the dynamic software environment?
Well, the risk is apparent and very costly. We have examples where so what really happens in our industry is that we go out and we make a survey, we make some exploration, we look for oil, we acquire subsurface imaging, and then we try and interpret that in various ways and figure out whether a little blip means that there is oil or gas in there or something else. At some stage, we are going to decide to drill down towards that, whatever we found on the subsurface imaging. If we cannot guarantee that the picture we were looking at, we know exactly where that is on the globe, we are going to position our rig incorrect. And when we position an oil rig and start drilling, for instance, even if it's just 300-400 meters away, it's going to incur costs in the millions of dollars, possibly hundreds of millions. Some of the companies that I work for have done this. They spent 150 million on placing a rig incorrectly. One of the worst things you can do is drill offshore and drill in the neighbor's license block, for instance. So you're actually hitting oil that isn't yours. So yeah, it's very costly not maintaining geospatial integrity.
Yeah, it's very expensive.
One of the things in Sahara Desert, for instance, is that these are all conflict areas, so there is a lot of mines in the desert, unexploded ordnance and things, and that's also generally cleared with bulldozers, and we have cleared corridors where it's safe to be. But if you don't maintain your geospatial integrity, you end up being outside those corridors when you send out a survey team or drilling team. And we've had examples where they've run over mines and people died.
Yeah, correct. All right. As there are no further questions, so I want to extend my sincere thanks, Mr. Nils Lundström, for
Thank you very much.
His time and valuable insight during this webinar. We're pleased to present you with the certificate as a token of our appreciation.
Thank you very much.
All right. This is your
great
certificate. Thank you, Nils.
Thank you very much
for your time, for your excellent presentation. So on behalf of the organizing committee, I would like to thank you everyone for attending today's section. We hope you found it both insightful and valuable. So the next webinar is the third conference on applied geodesic engineering. Will be takes tomorrow, Saturday, 5 p.m. Venezuelan time. Luis Perez will present a webinar titled Artificial Intelligence at the Service of the GIS, Geos AI, a plugin for QGIS. This section will be conducted in Spanish. So for more details, please visit our social media platform at SIGGMA X, Y, and Z. Thanks again, Nils, for your time.
Thank you very much.
Well, this is it. Take care, everyone. See you tomorrow. Bye.
Thank you. Bye-bye.